Hey, Rust, okay. Hope you had a great day at the conference. I'm Shriram Balaji, and I'm here to talk about Rust Unlinked, a journey through compilers, symbols, linkers, and static libraries. So I work at Microsoft in the Microsoft 365 core division, and I've been tinkering with Rust since roughly 2020-ish. And so I very recently also made my first minor contribution to Rust C as well. So I'm a newbie there. And I've done at Microsoft. I've done. I've worked across the stack. I've worked in contacts. I've worked in Outlook. I've worked with UI interfaces. I've worked with mobile apps on Outlook Mobile, and more recently, I'm working on this team, which sort of helps orchestrate trillions of events across different services at Microsoft that are responsible for a wide range of things, including like meetings, calendars, and every day-to-day functionality of a lot of the Microsoft 365 ecosystem. Um, I've been doing that for roughly a year at this point. And my more recent interests are to read up about databases, systems, programming languages like Rust, and then I'm also starting to like and read a lot more about distributed systems. And I'm Shriram at Shriram Balaji mostly everywhere on like Twitter or GitHub, LinkedIn if you want to follow me. All right, enough about me. So the agenda for the day for this talk is to understand linking from a high level. And then we'll go, I'll have a very high level overview of what is happening when Rust compiles your code and what are object files if you've seen them earlier and what are symbols. We'll get to what symbols are. We'll try to manually link symbols. We'll look at something called LTO, which is link time optimization. And then we'll understand something about ABIs and stable ABIs and dynamic linking. All right. I think I threw a bunch of jargon right now, but I think as we go over the session, I think it'll be a lot more clear. All right. So understanding linking, right? Linking is basically you can think of it as the it is just a way to combine object files into an executable or a shared library, right? It's you can think of it as like putting together puzzle pieces to create a final working program, right? On Windows, you would get a .exe. On Mac OS, and the next you'd get something which is an ELF executable, right? ELF being the executable and linkable format, right? And what linking is doing this in there's one piece of that what linking is doing. A linker does a bunch of different things like optimizations, but the main magic is something called symbol resolution, where the linker is able to match a variable and a function name to a specific memory address, right? So making sure that that everything actually fits together, right? Cool. So now, why is understanding linking actually even necessary, right? Like, why are you even talking about this, right? If you look at major Rust projects, and if you've talked to folks who are involved in large projects specifically, linking is often a big part of compilation time, and more often than not, when you hear people complain about compilation time, inherently there is a good chance that a huge chunk of it is going in linking, right? And if you look at large projects, I'm taking this from one of the articles that the Rust team had shared, where they moved their latest linker to LLD on Linux platforms, right? To use the LLVM linker by default on Linux platforms. And also, if you look at, I think ripgrep, if I remember correctly, RG for short, which is a very popular project in the Rust ecosystem, has also had some documentation that mentioned that roughly half of the linking time half of the compilation time could be spent just in the linker, right? So this is a real impact in terms of the compilation. If you want to have some sense of understanding of what is actually taking so long, I think it is a good way to understand linking so that you understand what is actually going behind the scenes. So a compilation is basically just you can split that into two steps, right? The compiler compiles source code into into object files. Not necessarily again that is some sort of an oversimplification, but yeah, a compiler does compile source files, and then the linker takes all those files and then combines them into a single executable or a shared library, right? Again, this is oversimplifying. A lot of modern compilers have a lot more things to do. I'm just to get the basics of it. This is what it does. So, but before we get to linking, the first we need to know a little bit about the first stage, right? We are saying we need to know about compilation, right? And I'm going to specifically talk about the Rust compiler, right? And as I already mentioned, I'm a newbie rustc compiler dev, so and I've done very minor contributions to it in the 1.8 1.83 release. But still, there might be certain things that are either oversimplified or reduced to a format that is based on my understanding, right? So that if there are any inaccuracies or certain things that need to have a lot more ones, please feel free to chat on all the or just put a comment on any of the platforms that I mentioned from earlier, and we can have a good healthy discussion. All right. Perfect. So we'll look at a high-level overview of Rust compilation, and we'll try to do it in a simplified fashion, right? And all of the steps that we are seeing in this compilation pipeline are presented linearly, just for the sake of clarity, right? And the actual implementation is not all of these steps do not happen linearly in the sense that it is not step A and then step B and then step C. It doesn't happen like that as of today. It is based on an implementation called as query-based implementation, right? We'll get to what I'll also give you a gist of what query-based implementation is. But let's get to what is the first stage, right? So when you the first step that happens is your source code, right? We have a simple main.rs program, and the first couple of steps that happen are lexing, parsing, are lexing and parsing, right? So in the lexing stage, what happens is there's something called as a lexer, which is defined in the rustc underscore lexer and the rustc parse underscore rustc underscore parse lexer. These are two different sort of functionalities inside the Rust compiler that convert your source code strings into parsable token types, right? And these parsable token types, what happens there is that the parser takes those tokens into a format, into a structured format called as an abstract syntax tree, right? So when I said in the first step, when Rust takes your what the Lexer does, and it takes the strings and converts it into tokens, but they are not directly consumable in a format that is ready for further for the further steps in the compilation. So what it needs to do is convert the rustc underscore pass has its own lexer that converts into more concrete types that can be further converted into an abstract syntax tree. And if you look at in terms of most modern day compilers, or I think even slightly going way back also, I'll also take JavaScript as an example. When the compilation usually converts these into these stages are generally common in most compilers, right? There is the lexing stage, there's the parsing stage, and then it usually converts into some form of a tree structure, and that is an abstract syntax tree. So the AST's job is to mirror the structure of a Rust program in memory, and it uses something called as a span to basically link every a particular AST node back to the source text, right? So if you have, say, a particular print line macro that you are saying, in the abstract syntax tree, you'll have the exact information about the print like macro that you're seeing over here, and where it's in terms of line offsets and width and things like that. It doesn't particularly track the source code line directly. It might have that as some sort of metadata, but this is mostly tracked in terms of offset. All right. All right. So once from the AST, it is actually what happens is we need to simplify this into or rather simplify, we need to lower this into a different intermediate representation, right? And we're going to see a bunch of intermediate representations that are going to come throughout the compilation pipeline, right? So what happens with this HAR is during this lowering, what happens is the Rust actually expands macros, the macros like the ones the ones that are I mean I think you know what macros are at this point. It also desugars syntax, like for example, if you have an if let statement, it desugars that to a match statement. It performs like name resolution and dissolves imports if you have different module level imports or things like that. All of that happens during this lowering. So this before you get the actual high level intermediate representation, or otherwise called as the HIR, all of these steps happen. And then with the HAR, what we do is the type inferencing. So type inferencing is basically if you say if you have let A is equal to 20 or something like that. On I think on modern platforms, it would I think on 64-bit architecture it will go and then store that in a I64 or U64, right? So all of the automatically deducing the types of the variables without you giving explicitly specifying the type all happens in this with the HIR. And then it also does trait solving. So what does that mean is if you have multiple implementations of a trait for a given type, it has to find the correct implementation, right? All of that happens in this step. And then from the SAR, there's something called as a THIR, which is and then which is a typed HIR, which has more type level information, which is even further lowered into something called as a MIR, right? And the MIR is important in the sense that MIR is where the borrow checking happens, right? If I remember correctly, if I read through correctly, I think it used to happen at the HIR level, but I think more recently it's happening at the MIR. Like I think, correct me if I'm wrong. So the borrow checking is where I think you're since we are at a Rust conference, I think everybody knows what the borrow checker is doing, and all the ownership rules and all of the emphasis on the ownership rules happens at this with the MIR. So whenever your Rust analyzer or anything is throwing an error, it is basically coming bubbling up all of that information from the borrow checker, right? So the borrow checking happens here, and it also does something called operator lowering. If you're implementing, say, an add operation on like two of your own self-defined types, like for example, right? So if you're implementing an add, and if you want to have two of your own types, and if you want to use the plus operator, and if you want to implement, if you want to implement plus operation for that, and if you can have your own add function that does that for you. And during this phase is when that operator lowering actually happens. And monomorphization, I think this is probably something that you've heard, right? Like say for example, you have a function that takes in a vec of t, right? And your only use case of that function is to sum a list of I don't know, so sum a list of 32-bit integers, right? So if that is the case, and you don't have any other implementation of it, uh, what Rust the compiler is going to intelligently do is monomorphize that into the actual concrete version, right? So that even though you have written it as a generic of vec of t, but when you're actually when you're calling it, you're only passing it as a function that has that takes in a series of integers and then sums them up, right? So it doesn't particularly have to have all the variations of it, right? So, but in other languages, you'll have the compiler usually has to generate multiple versions of this, or has to do dynamic dispatch, which will particularly it will reduce the compile time, but it increase the runtime of that particular of using that utilizing those generics. So Rust does this important thing called as monomorphization, right? And it is a fancy term to get started with, but it's just generating specialized code for each type that a generic is called with, right? All right, cool. After the optimization of the MR, then needs to get ready for the actual code gen phase, right? Code gen is basically where the magic needs to happen, right? So the code gen here is your code is actually converted into split into small units called as code gen units across the different crates, and then by default it uses LLVM for code gen. There are also other code gen backends. I think there's also a GCC code gen backend. There's also an SSA code gen backend, which is the code gen backend, which is supposed to be platform agnostic. So that is also there. But by default, let's consider LLVM for this purpose, right? So what is LLVM? LLVM is this tool chain that it's a project that contains a modular, a reusable, and a pluggable compiler backend. So I mean, if you're coming from web development or some other areas, I think you understand the concept of a front end and back end, right? Similarly, compilers also have this concept of a front end and a back end. So the compiler front end is what you mostly interact with, which is your you write source code to it, and then the source code gets converted into the stream of tokens, and then the lexing and parsing and the AST and all of the lowering and all of that happens. The backend is what actually triggers your um, excuse me, just a quick second. Yeah, and the backend is what triggers your the backend is what takes in the intermediate representation, and then does a bunch of things to it, and then finally you're able to get the binary executable, right? Your exe or whatever the program that you're running based on your target platform, right? So that's where we are right now at. So right now, before after the end of the compilation, we are at this phase of find this phase called as an LLVM IR, right? So NLVM intermediate representation. All right, cool. let's do a quick detour, and I'll show you a very simple, small sample program, and then what does that sample program look like, and what does the LLVM for that sample program look like? All right, so let's go here. Okay. Um, Again, it's entirely okay if it is something that is a bit too much to understand, but I'll try to be as concise about it as possible. All right. So here, let's ignore these for now because I'm going to this sort of, and I am shadowing it this a little bit because these are things that the same program that is going to come up a little bit in the future. So here you can think of this as a static mutable variable called global, which is a 32-bit integer just assigned 5. And then there's a function foo, and then there's an unsafe block, and then it is mutated to a 10, right? It's a simple global variable that we are mutating. And the reason this has to be unsafe, it's an unsafe block is because there's a static mutable that you're mutating, right? And then there is no safety guarantee because you could potentially run this from across threads, and then there will be multiple threads trying to access the same global mutable, and then you will have a race condition, right? So that is why you most likely have to put this in an unsafe block, right? Cool. I think it's pretty straightforward. And you can use this command to actually generate an LLVM. So instead of using cargo, which is what we are used to, we can still use that. So you can do cargo rustc as well. Or when you use Rust up and install the Rust compilation toolchain in your system, you also have the rustc binary, right? So you can do rustc emit LLVMIR and src/foo.rs, which is the name of the file. You'll get something called as a foo.ll. Right, LL is the LLVM intermediate representation, right? And you can see it looks very similar to assembly code, but it is not entirely. I mean, it's not 100% human readable, right? But you can think of it as being very close to assembly, right? So let's say here what it is doing is basically you can see that there is an add global. It's saying that this is a global identifier, and it is saying it's a 4 into I8, right? So basically, but it's trying to align this into. It's trying to do this memory alignment thing, right? It's trying to align this across four bytes, which is because it's a 32-bit integer, right? And we are using only because we just have 5 stored in it. It's not the rest of them are all marked as zeros, right? All right, cool. And then this DSO local is basically something called, this is a local function that we are describing, right? Which is the foo function, right? And this marks the start of the function. And what we are doing, if you remember, we had a global variable that we are updating from 5 to 10, right? So if we are storing a 32-bit integer called 10 in the pointer that points to this global variable, and then we also have to make sure that is aligned to that has a four of a it is aligned to the memory ordering that we already have, right? I don't think these are all particularly useful. Some of them are target specific. These are all module flags that, honestly, I don't have a lot of idea about. You'll also have some metadata information into all of this, right? And if you remember from the last, this is going to keep recurring. We see this thing called CGU. CGU is a code gen unit, right? And if I think I told you like a couple of minutes back that in the code generation process, the creates are sort of split. Your code is split into small chunks called as code gen units that are parsed by LLVM in a parallel fashion, right? Yeah. Okay, cool. So let's go back. I think this is what I think this should be. This is a good enough detour, right? Let's go back. So after what happens is I'm just going to rush through this a little bit because I don't want to spend a lot of time in compilation because we have a lot of stuff to cover in the linking phase itself. All right, cool. So in code generation, it involves generating the machine code for the specific platform, and the LLVR is just as I told you, it's already assembly. Like LLVM also does a bunch of optimizations and then spits out the final object file, which are then passed on to the linker. And the linker on Linux and on Linux, I think as of May 2024 is using the LLVM's linker, but on Mac OS and Windows, it's going to use either MSVC or LD64 on Mac OS and an MSVC on Windows, right? So those are the system linkers. But if you remember, again, so just jumping up back a little bit, I still have a little bit of to talk about. all of what I showed you is realistically is very step by step, right? If, there's step A, there's a lexing, parsing, HST, sorry, lexing, parsing, AST, and then the MIR and all the lowering, and then LVMIR, and then final executable, right? I showed you a sequence of steps, but that is not how it is actually today, right? There's something called as demand-driven compilation where there's a query, and then this something it's a query-based compilation. So what a query-based compilation is basically is that there is a compiler database, which you can think of it as an index of some sort. It is a database, right? And the compiler database has the knowledge about uh, the specific crate that you are dealing with, right? And that's what is called as a compiler database. So what will happen is basically you'll have a query. You can think of this as a function call, or just probing the compiler database for specific amount of specific information, right? And this specific information each query will have all of these parameters: is the name, the key, the result type, the query modifiers, and the provider function, right? So every step that we saw from earlier is actually modeled as a query instead of it being a sequential process, right? So if you take a look at trait solving, I told you with the HI we do something called as a trait solving, right? So if there are multiple implementations of a specific trait, so this is again taken from the Rust compiler source code. So here this is what a query looks like. This is a query key keyword, and the name of the query here is the implementations of the trait, right? And the query key type is a create num and a defined. I don't want to particularly go inside what these are doing. And there's a result type, which is the TCX here points to the if I think if I remember correctly, this has to do with something. This is the context. This is the context lifetime. And then there are query modifiers that want to get added. Again, the actual implementations of this is not particularly relevant for this talk itself, but I'm just trying to give an idea of what a query looks like. So you can think of this as just a function that takes in a bunch of arguments, right? That query the compiler database of specific things, right? And then from that, from all of these results that come from the function call, right? Let's say, for example, I can ask the compiler database of all the traits. That is what we were doing. All the traits of the specific type, right? I can query the compiler database about a lot of different, even metadata about the crate and things like that. But so all of that is present inside the compiler database, which is built up, right? And the results are actually memoized so that when you have incremental compilation, so basically you're writing code and then that gets automatically compiled with things like that. Or when you are invoking cargo again, I don't want to do a fresh build every time, which is used to be the case, I think, long ago. Now you have incremental compilation, and effectively once the first compilation is what usually takes a lot of time because it's pulling in all the crates, and then eventually after that, things are much faster because of incremental compilation. Right? This enables faster builds and things like that. So that is what is demand-driven compilation. I think I gave a very, very high level overview of it just because it's not particularly relevant for this talk, right? All right. So I think that's enough about compilation. Let's go back to linking, right? So there is a step where object files are, I told you that there's a step where object files are generated and then later linked, right? But what is in these object files? An object file, it basically contains machine code or byte code. I'll get to the byte code part of it, as well as it can have other data or metadata that is generated by the compiler or the assembler from the source code. Right? The machine code that is generated is known as the object code. Right? I think that is the Wikipedia definition that I showed you. So what we are used to if you're used to writing C, we are typically you can link object files together by just passing them on to the linker, right? So you can do GCC hyphen dash C, and then you would get the compiled object file, and then you can pass it down to the LD, which is the default linker in Linux, and then you'll be able to link these two object files into the foobar output, right? So as an experiment, what I tried out is, can we try do something? Can we try doing exactly something like that in Rust, and basically compile two independent files and then passing it on to our linker directly, right? And let's see if we can actually do that, right? So if you remember the foo.rs I showed you like a couple of minutes ago, I think like yeah, 5 or 6 minutes ago. So here you can see that. I think as I showed you, right, there's a global variable. The goal is that there is we import a global variable from foo.rs in bar.rs, and then now we are mutating it to 20. Right? So the no main attribute, what it does is tells the compiler that there is no main function, right, and effectively not to throw a compiler error when it does not find one. Right? And the no mangle attribute disables this thing called mangling. So what's mangling? So when you have Rust code that is compiled, right, identifiers are mangled. I think what compilers do this in intelligent trickery is that if you have symbols of or variable names of specific names, and you want to avoid name collisions across the area, across libraries or across other things that the linker has to link to it. So in order for it to be easier, what to avoid these collisions altogether. These names are transformed into a different, it looks like mostly garbled text, right? So here you can see that the global variable that we saw from here will be garbled into something that looks not human readable, right? So this is so that as I said, this is to avoid naming conflicts when linking with other libraries. So that is, but we want to disable mangling because we want to actually, if you see on in bar.rs, we want to refer to the global variable by name instead of assuming what the actual the dependency is going to be. We are going to give it by name, saying that I want a global variable that exists somewhere. All right. And the extern C block is only telling the compiler that the global is defined elsewhere in a foreign library and it does not particularly know where it is at. So extern doesn't mean that we are interoperating with C, but rather using the C's ABI, which is the application binary interface. We'll get to ABIs at the end of the talk, right? And so what bar.rs here is doing is that it just assumes that there is a variable declaration for global that is present in a foreign library somewhere else, right? That is what is basically here. That is what is basically happening here. And this is what you would call as a calling convention. So you're saying that when you have an external block in Rust, you're specifying a calling convention for a specific invocation for something that does not particularly exist here, right? Right. And this, I think that I already explained why this block has to be unsafe, right? And if you think about this in the context of even FFI, right? Uh, Rust cannot guarantee safety in terms of foreign function interfaces, even if the foreign function is present in Rust, right? Because we are especially because we are trying to link together them statically. I will get to what static linking is, and this can be and the global variable is available in an external contract that the bar environment does not know about. So there is all of the memory safety guarantees are out the window at that point, right? So we are trying to mutate a globally static variable imported from a library which cannot be memory safe, right? So that's the reason why that block is unsafe, right? Okay, cool. So since we want to invoke the linker directly, let's not use cargo for now. So we'll use again trusted Rusty to emit the object file for foo.rs and bar.rs, right? And once you emit that, you're going to get two files, foo and bar.o. Let's just try that. Yeah, so emit obj. Oops. Let's see. Yeah. So you can see there is a foo.o, right? It is this is not something that we can open on the editor per se. So yeah, let's not do that. But how do you actually even open it? What is inside them, right? That's the next part. It has something. Just a disclaimer: that an object file has a lot of different things, and it's usually in Mac OS and Linux. It is something in a format called as an L format, right? Um, and the L format is basically an executable linkable format, and the symbols are specifically stored in sections of this object file, right? And in Mac OS, it's called as a Mac-O object, which is syntactically very similar to ELF. And in Windows, it's called as the portable executable format or the common object file format. They are interchangeably named, right? So if you want to actually view what are the symbols that are there inside it, we can actually try doing that. So let me clear up a little bit over here. So we can do nm foo.o, and we can see the same thing here, right? So here, what are these symbols? What are these things that we see here? So here, if you see, D here represents a global data section. Uh, T represents a global text section. The lowercase d represents a local symbol, and the lowercase s represents an uninitialized local symbol for like small objects, right? So what is it telling here is that there are places or there are areas in the object file that are specifically demarcated for different types of data, right? So here, the function that we are declaring, the name of the function that we're declaring, which is the foo, which goes inside as a text symbol, whereas the variable that we initialize, which is the global variable that we initialize, goes inside the data section, right? And if we have any, and the ltemp0, ltemp1, and ltemp2 are all temporary symbols that are generated by the compiler during compilation. Those are not things that we explicitly added ourselves, right? So those are not actually present in as part of our code. Those are also things that the compiler generated. I mean, if and the, bar if you do bar.rs also, you'll get something very similar. So we can try that again as well. So and then we do nm bar.o. Now, interestingly, we see this. We did not talk about U, right? We did not. There's this symbol called U, right? And this is it's called as an undefined symbol. So basically, what is happening is, if you remember, the bar.rs has a reference to a global variable that it does not know where it is, right? And it is the undefined sort of section is where the global symbol exists, right? So the undefined symbol reference is very important because this is basically what is happening is that the compiler is saying, I've compiled this file for you. I will add a to do for you in the object file saying that there is a reference, I don't know where. It's up to the linker to figure out where that reference is. If it cannot find that reference, then throw a linker error. That's what is going to happen, right? Cool. And I spoke about the executable linkable format, right? So I told you that the object files are in a specific format, and I talked about sections. This is what those sections actually look like, right? So the elf header, which has all the metadata of the object file, all the assembly language code that we write is inside the text section, right? And all the read-only variables are in the our data section. All the read, write, and global variables, like the global variable that we saw, which was set to 5, is set inside the data section. There's something called as the BSS, which is a block starting symbol. This is basically an optimization that is done to save space instead of allocating, like say, for example, if you set a variable to 0, instead of explicitly allocating that to in the data section, this will just say that this particular, there are symbols that, start with 0, right? Symtab, which is a symbol table. This is the representation of the, when you did the nm command from the previous slide, this you actually using this to show that, right? And there are relocation entries for text and data section. This is basically the to-dos that I was talking about, right? So the missing symbols that are later fixed by the linker are also present in this section. We did not particularly see this because I think the undefined will have a reference in the relocation entries. And if you're used to any sort of debugging experience, you've written a breakpoint or some sort of things like that. And if you're used to a debugging, if you're used to using a debugger, uh, all of these come into play, which is the information regarding the stack local variables, or the mapping between the assembly code to the line number of the actual source code. The dot line is actually where uh, it tells you where the actual, if you have run into an error, the assembly code needs to be mapped into a particular line and things like that. So that is what the an executable and linkable format ELF file looks like. And if you look at in terms of in Windows also, the format is actually not very different. And Mac OS is very actually much more closer, I would say. So the underlying fundamentals of how an object file works across platforms is very similar. So having a baseline understanding of that is very helpful, right? Now, now let's actually, if you now we have two different functions, foo and bar, right, and two different files. Let's create a main.rs to actually link them both together, right? And then we will, as we did already, we'll just emit an object file and then create an object file out of the main.rs also. This is what I wanted to try. So this is the experiment. Basically, I want you to think for a quick second, right? We tried to actually link these. We said that in C you are able to link two different independent source code using just from that are taken directly from the GCC compilation. You have object files that you're able to directly link. Can we do this here? I mean, if you think for a second, it will become very obvious of what is going to happen. But this actually blew up in my face, right? So this is sort of not that the ending that would have thought for all of the not the payoff that we would have thought for, right? So we did so much, but we got an error. I think that is the sort of the story that we have to keep going, keep coming across with Rust, right? we have to embrace the compiler errors as we write more and more Rust is what I've learned. And the compiler is your best friend. But here, what is happening is here basically, if you sort of squint, you can see that the standard core that std core ops function once call, right? Call once is not present, right? So basically, we are trying to do a reference to a standard library which is not there. This is because when standard library is actually linked, it is linked as an rlib file. It is not. It is linked as rlib, and it comes through your Rust source code automatically. I don't know if there is an actual way to actually start. I don't think it is statically linked, because if I remember correctly, it is dynamically linked with your Rust source code, right? I don't think there is a way to statically link it, but I mean, if someone finds a way, that will be great. But so that is why I was not able to use the LD linker to directly link all of these two together. All right, but Rust actually has a way. Instead of going through all of this, we could have actually done it in a much more simpler way, right? And that's what I'm. So why did we go through all of this pain? Is to try to replicate the exact experience that you're seeing with C in Rust, and then trying to see if understand linking from just by passing it to a linker. We understood that that is not particularly something that we can directly do. So instead, what we do is we use the ecosystem, right? So the Rust C already has has a support for this crate type called as a static lib, right? So when you say there's a static lib, you can specify something as a static lib, and then you will get a static library into an archive, which is that is a .a file. So it's basically in all Unix systems you will see, which is it is a huge. You can think of it as a zip file of all the object files that are there that are comprised of all the static dependencies of that particular foo.rs and bar.rs, right? So this will automatically pull in the core crate and bring in the standard dependencies that we want, instead of us trying to actually go and manually link it, which we could not do in the previous step. Right, and once you do that, you can actually just go and open you can use the AR command to open the .a files that I showed you, and it will actually have all of the object files that we saw from earlier, right? You can even, do the nm command on those object files, so you'll see the exact same symbol tail that we saw from earlier, right? Cool. So, but I think all of this is very cumbersome. So what we will do is we can write a build script in Cargo, and then say I'm going to put these foo and bar in this target out folder. So you go and manually search for them in this folder, and then link them together, right? So that is what the link lib static foo and link lib static bar actually tells the compiler to do, right? You can also have a slash link in the attribute in the build script, and that is basically the same as doing this, right? You can add that in the main.rs instead of a build script. That also works. Cool. Now, I think I'll speed this up a little bit. We'll talk about link time optimization, and then we have a bunch of stuff about ABS to cover with. All right, cool. So link time optimization is basically where in typical when there is no what is link time optimization? Basically, when I told you about the step about compilation and all of that, and the LLVM tools and everything, if you remember the diagram for like 15 20 minutes back, uh, uh, the when the LLVM IR goes into the to the tool chain, there is an important step that happens is what is link time optimization, right? But when there is no link time optimization, what basically you can think of as happening is you have your source files which are compiled and optimized. All the optimizations include all the compiled optimizations that I was talking about. You get the object files which have the machine code in there. So machine code is basically all the which is effectively machine code that is compiled for the target platform, right? For the target architecture, and then they are linked together, and then you get the binary executable. Like this is the straightforward way of doing it, right? But with when you have LTO, you can increase your compile time can be much drastically reduced because of LTO, because it's doing a much more optimizations to make sure that your final executable can be more performant in some case. But LTO does not particularly guarantee more performance. There's a good chance that your compile time might drastically increase also. So let's look at that. So when you want to disable LTO in the RUSI, you basically, you can do you can pass in -c LTO off, or you can there's a profile setting in cargo.toml. Where you can set it to off, or they can say no n or anything like that, and then disable LTO, right? But the important part is, to set it to false, there is a very peculiar behavior that I noticed, that if you pass false to the command and argument, it turns off LTO as you expected. But if you pass false in the cargo profiles, it does something called as a thin local LTO. It doesn't actually turn it off. I am still, I still don't know, have enough clarity to understand why this is the case and why the same false. This is based on the documentation that I'm reading in the cargo profiles page and a bunch of other places. So this is still an open question for me, and why false has such a peculiar behavior, right? The next type of LTO is called a fat or a full LTO, right? So this is where what is happening here is the this is going to do a instead of your object files having the machine code, your object files are going to have the intermediate representation. In our case, let's since we are talking about LLVM mostly, this is going to have the LLVM intermediate representation in bitcode format. So what is the LLVM bitcode is basically just a container format or like a binary format for the LLVM IR that we showed earlier, right? You remember the IR that we saw, which basically look like assembly. Think of you squashing that into a bytecode format, and that is basically what is an LLVM bitcode, right? And that is present inside the object files, right? And all of them are actually merged into this one huge module. So why is it called a fat or a full LTO? Is basically uh, the in fat LTO, all of them are merged into one huge LLVM module, right? And then you run optimization on top of this. All of this happens on this on a single thread, and that's why fat LTO is probably the most costliest link time optimization that you can do. You'll get your code, your final executable is probably going to be very optimized, right? But the cost is much higher in terms of the compilation time, right? And that is why this is something that you, if you're doing, you'll have to be very sure of why you're doing this, and you need to have like an absolute need of why you're doing this. Otherwise, if you're running your compilation in CI or something like that, and you have fat LTO, things are going to blow up, right? It's going to take a lot of your CI time. You can use the fat argument or in the LTO profile and things like that. If you say yes or on or true, it goes to fat. I think these are all there for historical reasons, just to avoid breaking how cargo profiles work. If I'm not wrong, but again, this is very confusing, right? The other much more performant thing to do is something called as a parallel LTO. I think something that I think 15 or 16 was introduced in LVM, if I'm not wrong. And so what parallel LTO is here is doing is instead of instead of actually doing it in as a one huge module, what it is going to do is it's going to compute just a summary or some metadata in an index, right? And then from that index in the linking stage, we are not going to actually link. We are just going to get some specific information about the specific module that is in question, right? It will basically, let's say if you're talking about the food or whatever is the code gen module for that. Again, I'm talking in terms of files, but you have to sort of imagine this in terms of just code gen modules, right? All of these are I'm just showing as files, but these are also you have to think of them as individual modules and individual units, right? Or basically you can think of, if I think individual modules makes a lot more sense. So when that is linked, they're not actually linked. That goes into a particular index, and that global index of functions is what is being queried and then optimized in parallel. So all of this, you have the thin LTO. When thin LTO kicks in, your whatever your the compiler backend, in our case LLVM or LLD, which is the linker, which basically spawns off a bunch of threads to do all of the linking and the optimization independently for each of your modules, right? So this is why this happens in parallel, and this is much faster and optimized, right? So that is why this is also generally a preferable way to do it. If you say thin or in your cargo profiles or your command argument, you'll get that, right? The next alternative to that is called thin local, right? So as I told you that since we are splitting a crate into multiple code gen units for parallel processing, this sort of prevents optimization if they are not separated into different code gens, right? And that are handled independently. So thin local LTO is what we do is basically we do thin LTO, but on a single local crate, right? So which brings back some optimizations that we might have lost. And this is the default in release mode, or when you say LTO equals false. So this is what was the misnomer that I was the peculiar thing that I was talking earlier. So when you say LTO is false, it doesn't turn off LTO. It actually does the local LTO for you. This is something that you'll have to note, right? Your LTO is not entirely turned off even if you say LTO is false, right? So yeah. let's get okay. So now we'll talk a little bit about static linking and dynamic linking, and then I'll try to wrap this up very quickly. So static linking is basically, I think, it's sort of a refresher from something that we have learned from earlier, which is basically static linking is where all the necessary dependencies are compiled and then linked in the final executable statically. You can either, this is why you can, if you make a Rust executable by default, it's easily distributable and things like that. And dynamic linking, on the other hand, is requires external libraries to be shared libraries into memory, and they're used and use their functionalities that are required at runtime rather than at compile time, right? This is something again. So Rust statically links everything, including your local creates and everything, and promotes more. You could say in some sense promotes static linking in some sense, and that is what is preferred for your crate levels and things like that. So the usual way of doing it is linking everything statically, right? Except dependencies like libc, which it cannot link statically because it varies from from platform to platform. Everything else is linked statically, right? So you could say in some sense that Rust prefers static linking, but if you think about it, why can't it actually do it dynamically? C is able to do it dynamically. C++ is able to do it dynamically, and they all prefer dynamic linking. That is the one of the main reasons is because Rust doesn't have a stable ABI. When I say a stable ABI, so ABI is basically application binary interface, right? What it does, it specifies a layout for your data that is in memory and the function call mechanics, right? So how a function should be called and how the data is laid out in memory is what is specified in the ABI, right? So in case of C ABI that we saw from earlier, that is the ABI, the specification for interoperating with C, right? Or C specification of how the memory data needs to be laid out, right? So the functions calls that involve complexities like register predicting registers or passing order of arguments are all called calling conventions, right? So if you don't specify a represent, so this is the idea of specifying the data layout in memory is called as representation. So and in short form, you have this attribute called repr in Rust that you would pass. If you don't pass that, or you have like an external calling convention, the compiler is free to optimize. The Rust compiler specifically is free to optimize how things are laid out. So if you have like a bunch of structs that where fields are ordered in a specific way and they are not particularly aligned in memory, means see that the memory is aligned the way you define it, right? There is no optimization there at all. So if you have a struct that has an integer followed by a float and a boolean and does not particularly uh, fallen with the specific alignment, it will automatically use that particular padding and then align accordingly. But here, what Rust will do is it will do the alignment for you. And that is, and if you do the alignment, if it does the alignment for you, the problem that it poses is that uh, different compiler calls leads to there'll be ABI disagreements as to how things are ordered in memory, and that is why dynamic linking is not a possibility, right? I'm not saying it's not a possibility; it's not something that it is preferred. You can still do dynamic linking. Actually, if you write, if you instead of if you saw there is a cdylib created that you can use for dynamic linking, but a stable not having a stable ABI is one of the reasons why you see a lot of static linking within creates at least, right? There are other libraries in the ecosystem. I'm just going to talk about that very briefly. There's a library called Stabby, which addresses this problem. What it does is it pins the ABA for a specific portion of your program and tries to do some sort of layout optimization provided by the. That is an unstable ABI, but it does so optimization, but it assists that by pinning an ABA for a specific portion of your program, right? So you can annotate your structs with this stabby attribute. It automatically struct becomes repr C. So when you say repr C, it basically what it means is it follows the memory layout of how a program, how a struct or an enum ordered in C would look like in memory, right? It will also there is an internal istable trait that is implemented on top of your trait. So this is what is enabled. It allows you to do like certain need optimizations and enums and things like that, right? And this is what a stabby code looks like. I don't particularly this is not important as to how this is working or going into details of stabby per se. But I'm just sort of explaining that there are options for having a library for standard for a stable ABI. And if you want to do dynamic linking, that is a way. But again, I think that is a disclaimer that for Stabby, as of right now, you need to use Rust nightly, right? Or use Rust before 1.78. So that's the requirement. So I think I've that is the end of my talk. And I've all of the references and the slides and all of that. I'll be able to share it in some form or the other. And all of these resources were immensely helpful in for me to write this down, first as a blog that I started, and then eventually I was able to build it up. This is talk. Um, and specifically the talk by Philip, the talk by Matt Godbolt on the bits between bits is a fantastic one, which talks about the same concept of in the context of C++. And a huge thank you to Ryan Stinnett, who wrote a wonderful article about link time optimization, and had a great I had a good chance to talk to him about this, and then get some. We had a very deep conversation about link time optimization, that where I was able to clarify a lot of things and assumptions. And all of these are really great resources to learn. And yeah, so hopefully you had a great conference, and hopefully I did not bore you a lot. So thank you. That's all from me.